So we are recording now. We are looking at homework 2, and so this is our governing differential equation. So we will first get the weak form. So over an element. So x e to xe plus 1. Um, so phi. Phi is the approximate solution. Now for the first one, we will do integration by parts. Since we are treating it as a bar problem, Therefore, this is so this is the dx is the force at the plane. Okay, so now we move all nodes and boundary terms to the right. So now we can
Nathan, on slide
uh,
number 2, the step number 2, you did integration by part.
yes, just a moment. I'm changing everything to plus now.
Okay.
Slide number 2. Okay.
To convert the weak form element, this last line, you did the integration by part.
This one.
Oh no, the top one.
Here I have not done as yet integration by part. Only this step is the integration by part.
Okay, thank you.
So now we will write, we are taking linear interpolation. Therefore, P is N1 XE plus N2 XE plus 1. And now if we move it to natural coordinate space, then phi is N1 the same, XE So in the real coordinate space, n1 is, oh, sorry, is n1 u1 plus n2. n1 u1 is 2. So n1 in real coordinate space is x minus xe plus 1 minus x by he, and 2 is x minus xe by h. And in natural coordinate space, n1 is 1 minus psi by 2, and n2 is 1 plus psi by 2, right? So if we look at the boundary term, so for n1, n1 boundary term, this becomes so force F2 at E, right? Because you will have, okay, let's write out the whole thing. So we have n1 at xe plus 1, dphi by dx at xe plus 1 minus n1 at xe and dphi by dx at xe. Oh, sorry, so this becomes 0, and 1 here is 0, and therefore this will become negative of n1 at xe is 1, so this will become negative of dphi by dx at xe. So, well, if you remember, if we take it by derivative, two is so F2E is set as um, x, right? So, so this becomes, because when we take positive slope, when we take positive slope, then these two are the positive directions of the force, right? We are assuming positive uh, tension, so elongation. So slope of v with x or slope of u with x, we are assuming positive, that is, it is elongating. So when it is elongating, you can imagine the force on the right has to be towards the right, the force on the left has to be towards the left, right? Then only then it will stretch. So that's why we have to give these two boundary conditions. There is a negative sign there. Therefore, if you go back there, this becomes F1 E. And for W is N2, N2 W dphi by dx at xa to xa plus 1 becomes N2 at xa plus 1 dphi by dx at xa plus 1 minus N2 at xe dphi by dx at x. Now we know that N1 and 2 are like that. N1 is like that. It is 0 at the left node, 1 at the, I'm sorry, and 1 is like that. And 2 is right. So this is 1, 1. So this is equal to N2 at N2 at xa plus 1 is 1, we know, and N2 at xa is 0, we know. So this becomes dphi by dx at xa plus 1, which is equal to F2e. So now we know that on the right hand side, the terms will be F1e, F2e, etc. for each element. So now that we brought it up to this form, we can go for the stiffness matrix. So, and that part we will do it in MATLAB. Let me start.
So, what's the value of phi?
Yes, so at this point we
What does it
don't know.
represent?
Yes, so Fe
Okay.
is the force on, right now we did the integral form over element E. So right now everything is for only one element, it could be any element. And this Fe is the force on the right hand side node F2E, force on the left hand
Yes.
side node is F1E. So now what we will do
Sure.
is, okay, before going to MATLAB, so now what we will do is we will write, sorry, not yet to MATLAB, we will rewrite this form now, and then you will see that we will rewrite this form into matrix form. Then only we go to MATLAB.
Okay.
Because
Sorry,
always,
I meant
yeah,
what is the what's the phi? The symbol phi.
Phi.
What does that stand for? Yeah.
Phi is the, yes. I'm sorry, I should put phi E. Thank you. Actually, it should be phi E. Yes, so you can change to phi. You can put superscript E. That is correct. And I will just say right now, E.
And the phi is representing like the change in the element.
No. I will tell you in this. Okay. So phi is, if you remember in the classical method of approximation, the first method that we did in the classical method of approximation. So what we do is we have the domain of the problem and we have a governing differential equation to solve over this domain, and we don't know the true solution. So we just assume that there is some approximate solution. And that approximate solution, which we will know, if you remember, we used to take phi as C0 plus C1x plus C2x square or some form, or plus higher order C3x cube. We used to take some form of the approximate solution. We don't know what is the true solution. So we are assuming an approximate solution over the entire domain in classical method of approximation. In finite element method, it is similar, but what we are doing is we have our domain, but we first broke up the domain into chunks, and each chunk or each piece is called element. Each piece of that domain is called element, and phi e is the local approximation of the function, or sorry, local approximation of the true solution over the element E. Right? So that's the big difference. That is, in classical method of approximation, you assume one approximation function to fit the solution over the entire domain. But in finite element method, you do piecewise approximation. For within each element, you assume one. So you can imagine that in the classical method of approximation, just let's say that your true solution looks like, suppose something like that, right? Suppose. Then you can imagine that in order to get a good approximation to this solution, we would have to assume like x to the power 4, x to the power 5, or some quite complicated approximation function, right? Only then we can really get a good fit to this kind of curve, right? But now imagine the same, this is the true solution, suppose. The true solution is like that. But now we broke this up into many small elements. Now I take linear approximation within each element, I can still get a not bad fit to the solution because it will fit like that. So when I break it up into elements, even a very simple approximation function is sufficient to solve the problem, right? To get a good solution.
Gotcha.
Okay. So that is phi e. Phi e is the local approximation to the true solution over one element. Okay. So now we will further we will simplify this now. So phi e is sigma J J over J, and W is Ni. So when we substitute these two, we will get the left-hand side term, which we call d phi. This is just usually left-hand side is indicated as b. That's all. So integral xa to xa plus 1 dni by dx and summation over j Mj. Let's take the derivative first. d phi by dx. This is sigma over j dmj by dx uj, because uj's are constants. dmj by dx plus c times p times w. Okay, this is um, and now we can almost, we are ready to move into MATLAB now. So this, sorry, here there is sigma over j. So like we did in the class, it is okay to interchange the integral and sigma. So bring the sigma outside, take the integral inside. J E. Okay, this is dx. Because this summation is over j and integral doesn't depend on that. So therefore summation can come out, and uj is again independent of the integral. So uj can come out of the integral. This plus summation over j integral xc to xc plus 1 n j c n j and uje, right? This is the left hand side. So left hand side we can rewrite left hand side we can rewrite as this is equal to kije uje, where kije is equal to sigma c to xc plus 1 okay. Now in this is b phi w, left hand side. In natural coordinate space, we know that x is equal to n1 xc plus n2 xc plus 1, where n1 is 1 minus psi by 2, and 2 is 1 plus psi by 2. This is a mapping from real coordinate space to natural coordinate space. This is mapping. So, so now Kij is equal to, psi goes from -1 to 1. And then we will get dni by dx is equal to dni by d psi times d psi by dx. So if we were to write that out, x is 1 minus psi by 2, xe plus 1 plus psi by 2, xe plus 1. So dx by d psi is negative xe by 2, xe plus 1 by 2, which is he by 2, element length by 2. So this is d ni by d psi times he by 2. So therefore we have d ni by d psi times dnj by d psi times dx is he by 2 d psi. So d psi by dx is 2 by h. So 2 by h. So 2 by h square times he by 2 d psi plus integral -1 to 1 c ni nj he by 2 d psi. So further simplifying, dni by d psi dnj by d psi a 2 by h d psi -1 to 1 c ni nj he by 2, right? So that is Aij. And right hand side, right hand side is right hand side is only function of w, so that is we call as lw. So this will become force term. This will become boundary term separately. Fe, fi. Now this one integral xe to xe plus 1 x squared w dx. This is integral -1 to 1 and x is equal to n1 xe plus 2 xe plus 1. So you substitute that. Square. Now this is ni and dx is he by 2 space. So now here everything is in natural coordinate space. We can go to MATLAB. Let me do a bit of something. I will do it at count. Just maybe 10 minutes I need. I need to do. I'll be back.
Oh,
Hello, Jamal. Sorry, I know you were just looking for a screenshot. Let me quickly look if I have. I remember I saved something on that day.
Yeah, I'll have to come back later because I got to go to graduation rehearsal now.
Oh, okay, let me quickly. Okay, these are the ones I have. Not this one. Oh, this is not even yours. This is but Jamal, I can do quite easily because I have your. You emailed me your SAP model. You remember?
Yeah.
Yeah, I can get it from there. I mean, after there, just for a representation, it should. I know you changed the forces, but uh, yeah, you have grid plus global on column. You're saying your most recent model got corrupted?
Yeah. So that one, I'm pretty sure that one has I think that one has all of like the wind loads and stuff on there.
So what is happening? It's doing something weird, is it?
Yeah. Okay, so I can show you
Okay,
right now. I have
okay.
so trying to get it to display the stresses.
Mhm.
Oh, maybe it's because it did it over here. I didn't see it over here. But if I go to one of the beams,
It's still doing, right?
it's loading on the zoom in. Froze.
Yeah, it's, oh, you mean you have to pick up all your gown and hat and
Oh yeah, I did that last week. This week we have to give them the cards for graduation,
oh,
and then we do the rehearsal at
oh,
9.
okay. There you go. Oh. Oh, actually, I have one more doubt. If any of you can help me. Uh, okay, you can right click on anyone.
Yeah, it's like the numbers are back small again.
Because it is the M2. You change it to M3, it should be okay. You
Oh,
right click once.
yeah, it's loading again because I
Oh,
changed it
oh,
to.
oh, okay. No, I mean, after you right click, you can change to M3.
Oh, okay. Yeah, I gotta wait for it to load.
Oh, one doubt I have, any of you, if you can help. I'm having some difficulty with degree works. actually for someone, and they don't update at all. So whom do you go to get that fixed? Because all the many courses that she actually, those are master's courses, they put it in undergrad, and then in masters they don't show it, and so it's all messed up. Oh yeah, you can do M3, first one. Is that not okay? A 91 kip for seems negative 91.
Is that okay?
That looks usual. It's a bit small. If you try another log combination,
Yeah, I think that's like the
yeah,
highest.
I don't think that was wrong.
Like, of course, that's
Yeah,
better.
just try live. Yeah, I don't think it is wrong, Jama.
Oh, you think that's fine?
I think so. You
Okay.
check. Yeah, I think it is mainly from gravity load. Oh, so that's good. Looks like the shear wall stuff worked, right? It took all of the weight. So basically, if you compare any of the beams and columns with wind load, without wind load, it should not look that different. That means the shear wall worked well. Yeah, hardly anything. See, because of wind load, hardly
Yeah.
anything. You try one column, try a column,
Okay.
you can cancel this one. You can try, yeah, for example, that one. Windex, you can try Windex, all the winds, you can see Windex, and nothing, hardly anything. Wind Y. Yeah, see, it all went to the shear wall, so that's good.
So when I'm displaying,
Oh, but the shear wall moments,
how do I go to that? Let's see.
yeah, that's in a different way.
Because I think we have to display differently for that one.
Yeah, I forgot now. Mm, just
Yeah, maybe show shells.
oh yes, display. Great. Yes, you got it. Now try to see M, not F11. You can do M22 and M33, M11 and M22. You can check those. Apply. Not
Think
so.
it is.
Where is the shear wall?
It's right here.
Oh, is it 2001?
Um,
I hope it's not hidden inside the curtain wall.
Oh,
Maybe you
you're
can
right.
do visibility and only shear wall. Yeah, select properties, area section, yeah, shear wall, select, and now view selection only. Okay, so no, it is quite small. Okay, but it could be because it's very big, so it's very wide, and so it should. You can try M11. Try M11. Apply. Okay, not that way. Oh, but the units.
It's in feet.
Yeah, I mean, this one is in foot per foot, I think. You
Yeah.
have to again multiply it. Oh, it's showing somewhere the unit. It's showing the unit anywhere.
It's showing the, well, maybe if I, yes, kip
Yeah,
feet.
keep foot per foot. See, keep foot per foot. So we have to again multiply with the length of this one is quite long, right?
Yeah.
So it will be maximum thing. What was the length of this shear wall?
Vertically it goes up.
Oh no, this. Let me.
Oh, like from here to here,
Here, yes. That.
probably like 30 feet or so.
Yeah. So you see, now you see there that the legend. Can you change to M22 once? M22 and apply. And the maximum was 3 point. Can you move this this window once so that we can see the legend? Yeah, 3.5 -3. Yeah, so you see that if you multiply by 30 feet, it's about 90 kip foot. So everything went there to the shear. So that's good. This is kip foot per foot, right? So if you multiply it with the 30 feet, then it is almost 100 kip foot.
Oh, okay.
You see?
Yeah, I get it.
So that's fine. That's fine.
Then this is the shear wall that we put in front of the, but we might not even have needed it.
It will help, I'm sure.
Yeah, it definitely takes off some load.
Yeah. Yeah. It should. Yeah, oh, this is taking a lot. Oh, this guy is taking a lot. Where is this one? That's a good.
This one, it might be a
That's
error because
Can
this
you-
one is supposed to look like, I don't know what happens to the other wall.
no, because Jamal, this is thin, right? So it is taking a lot. I mean, the intensity is a lot. Total moment may not be a lot.
Yeah, but that one's supposed to look like this one. So that's
It's
okay.
difficult because it's difficult to guess because the structure is quite.
No, I'm saying the wall though. Like it's
Uh-huh.
missing two walls. It's supposed to be a wall from here to here.
Oh, you're missing a. Oh.
Yeah, but that's all right.
Oh, that may be something off then. Oh, yeah, that is something off then.
Yeah. But the sides are uniform, so we'll just use
Then
this
that's
side.
why that is doing in plane. That is taking in plane. That's why it's so high. Because
Right.
those two are missing.
Right.
Okay, maybe you need to check why those two are missing.
I mean, if anything
That's-
were to take the other side,
Yeah, but that's not the purpose of wall, right? So
Yeah.
you don't want in plane. I mean, you don't want out of plane. You want like this, right? Not like that.
right?
Yeah.
These are the elevator cores. So I guess okay, I have to go to the
Okay. We
rehearsal,
can.
but
Okay, I
what
will
time?
also need some washing and come back.
So you would still be here, and maybe like I don't know how long it's gonna take.
I will
10
be
or
here
11?
because we have to finish the finite element. I will be here.
Okay.
Yeah.
All right, gotcha.
Okay. Ross, Bryson, I will just do something, maybe 10 minutes, I will be back.
All right. Okay. Congratulations, Jamal.
Okay. So, where here we stopped. So we got everything into the into natural coordinate space, and now Russ is back. Let me. Oh, here. Okay.
Yes, definitely.
Okay.
Okay.
Okay. Bryson is
Yeah.
back. Okay. So let's open. I think we made already one file, so we can reuse that file. So 1D bar 3 element, we can reuse this file.
Can you share the screen, Dr. Nathan?
Oh, yes. And let's reuse this file called 1D bar 3 element and MLX file. Let's make a new one. So save as problem. So we have all of these are same. Then Kij. Okay, Kij. I need to enter. Where is this is Kij. So let me just enter that. Okay. So derivative of Ni with respect to psi times derivative of Nj with respect to psi times 2 by He minus C times He by 2 times Ni times plus. We have plus. Let's make sure we didn't make any mistake. This is our original governing differential equation. Then this is minus and minus and this is, yeah, okay. It's fine. Plus. So Kij is correct. So let's just do it up to Kij first. So N is this, then K is, yeah, okay, that is K, all right. So we got element stiffness matrix. Now, domain, let's check domain of our problem. I think it's also 0 to 1. Let me save this. Now, it's 0 to 1. Ours is also 0 to 1. So this is okay. Domain size, discretization, 3 elements. So that's okay. Then HE numerical is H by 3, uniform. Each element is equal in size. Then 1 to 1 to number of elements. So connectivity, this is connectivity. So this one is just saying this one is just saying if I divided 0 to 1 into 1, 2, 3 elements of equal size, then this is element 1, this is element 2, this is element 3, and this is node 1, node 2, node 3, node 4. So element 1 connects between node 1 to node 2, element 2 between node 2 to node 3, and so on. So that means element E connects between node E to node E plus 1. So that was the node E, element K connects from K to K plus 1. Okay. Then nodal coordinates. So coordinates go through HE numerical. So 1/3. So for us, the coordinates will be 0, x is 0 here, x is 1/3, x is 2/3, and x is 1. So it will just go through like that. That's what we are doing here. Then L, let's check L. L is these two, so this one. So let's enter that. No negative sign. And 1 times XA, which is a square, times N times HE by 2. Yes, this is correct. And then we substitute HE and C. Okay. C is 1. Okay. And okay, now is the assembly. From here onwards is assembly. Just need to turn off one thing. Now this time only 2 minutes. I will be back. So we put everything up to here. Next part is assembly. So assembly maybe if 2 minutes.
Yes, Dr. Nathan.
Yes, yes. Sorry. So now we need to do assembly. So assembly, you remember, let me. So for one element in the form that we have right now, it looks like this. One. Oh, you can still hear me?
Yes, Dr. Nathan.
Okay, when this pen does this, that means the whole thing is, my computer is hanging. Oh no.
Okay.
You can still hear?
Okay. Yes, yes.
Oh, but my computer has hanged.
Do you hear me as well?
I hear you,
Okay.
but I have to restart the computer. Okay, let me join.
I think even if you restart, still gonna not will not take us out. So
No, it won't. Okay, let me restart.
yeah.
Sometimes this combination MATLAB, Zoom, plus
Yeah.
this, yeah, it just works. Okay, I will come back. I need to restart.
Thank you. For sure.